Hello, welcome to this webinar. June 2nd, it is 3 o'clock in Paris. This webinar is on chloride ingress modeling, the benchmark to chloride ingress modeling. And what I will present here today is are the results of this book. This is the book of the state-of-the-art report of the technical committee 270 SIM. SIM is from chloride ingress modeling. And that is what I will show you today. What we did, let's say the summary of the committee work. We have finally, after a couple of years, we ended up with a book which all contains all the information what we did during the committee. We started in 2016. I will present you that later, and we're able to simulate and compare and discuss the results of 14 different models. And I think the final result is really, really very nice. So the book looks like this to give you an impression. It's really a very nice book with lots of details, and although it is not so thick, it has not so many pages. Less is more, they say. It has about 80, 90 pages, and it's separated in a couple of blocks, main topics. That's what you see here, the content of the state-of-the-art report. So first, the introduction, of course, explaining everything, the idea behind this this whole committee, and also how we set up the state-of-the-art report. Then there is an overview of the chloride ingress models. Let's say some theory behind what theory do you need, mathematical formulations, right? So differential equations, how you can describe chloride ingress in concrete, in porous medium. And then finally also more details on the models we used. Then you see chapter 3 and 4, that is 3 is on marine submerged, that is how the chapter is called, and 4 is on road sprayed. So marine submerged is on concrete panels which have a constant chloride surface concentration, and the road sprayed they have not. They have only during winter they have a chloride load, and so that is differentiation we made. That's what I will present today. Finally, some conclusions, and yeah, that's it. That's the whole report. Of course, I'm very thankful to all the modelers. Unbelievable. We managed to get this team active and very active, providing all kinds of results, and with analytical models, with numerical models, discussing it. Yeah, it was very good. I think it was very good. It's really a reference work. What we can now, at least what RILEM can build further on. We started in 2016, as I told you before. Ended last year, 2021, last meeting, last committee meeting, and we also had this Corona limitation, 2020, 2021, and also the beginning of this year we had the last meetings. That was, of course, online. But in the beginning we started really traditional, almost we can say, committee work. This was in Darmstadt in 2017, where we started presenting the backgrounds of the models, which test cases, which bench cases, benchmark cases we need, and so forth, right? So you see here all the committee members. Yeah, so what I said in total, that's the RILEM page in the RILEM website. The TC 270 SIM is benchmarking chloride ingress models on real life case studies. That was the idea, theory and practice. And I was chairing this committee, and then my deputy chair was Kaiichi Momoto from Tokyo, University of Tokyo, University of Science, Tokyo of Science. yeah, you see here, we started in 2016, 12 TC meetings we had, active TC meetings, and of them were 5 online meetings. So yeah, let's say almost 3 to 3 per year. The benchmark cases are provided by Tang Luping and also Lars Olof Nilsson from Sweden. So benchmark, so they have this test case there, marine submerged. There are some concrete panels in the water, in the North Sea water. Here you can see it, west coast of Sweden, and they are there already for many years. I think 15 years, 17 years, and yeah, we could use that. We have all the information of that those panels, and we use that for the benchmarking. That was what we call the marine submerged. Then we have the road spray case that was provided by Jan Bishop. It's in Switzerland. There's this Bonadus field experiment. You see here 3 concrete panels. They are along the road. E1 is this one marked, and then E2 is that on the other side, and then E3 is the middle panel. And they are monitored already for 22 years. Actually, during the TC was running, they did another measurement. So we got the latest data on these panels. And yeah, these were the 2 cases we used for benchmarking. And yeah, what I said, this was the starting point. Why are we doing that? Of course, everybody knows, just a general slide on chlorides. They cause a lot of troubles in maintenance and concrete bridges, causing corrosion finally. And as you see here from this study, it was done by Professor Schissel from Munich, that it accounts for 66%. And if you also take their carbonation into account, you almost, yeah, it's really a major driver of concrete problems. Concrete cost, repair costs. Right, so where we start, when you look to chloride ingress, you start with the, finally with the mechanism. Yeah, the mechanism to describe the chloride ingress. And here we have a very simple description of what happens when you have a chloride ingress, chlorides entering the porous material, and which parameters are dominating this mechanism. That's of course what we need to know as modelers. So we need here the surface concentration, the chloride surface concentration, because that's our action, our load, the boundary condition. And we have here the diffusion coefficient. The diffusion coefficient is what of course determines the process. Finally, you have here the critical chloride concentration, but that's not what we need, because we only describe the chloride ingress, so we don't care here about the critical chloride concentration, at least not in this benchmark study. What we also need to know is the cover thickness, yeah, but that we can just take as a function of the ingress depth. So then we have no specific concrete cover thickness, what we need. Yeah, so that is of course that's rather simple process if you look to this. But if you want to describe it and you are with a group of scientists together, many discussions start. Which models do we need? Which kind of diffusion coefficient? Do we do the time dependent? What to do with the binding, the free chlorides, bound chlorides? Yeah, all kinds of details are very important at that moment. And those have to be answered, right? Before we start, they have to be answered. And that's what we did. We had here a meeting, 4th meeting was in Kowi, at Kowi in Copenhagen, a little bit north. And that is what we had as a discussion, and that was a very good meeting, I think, at this meeting, this 4th meeting, where we really fixed many ideas. Finally, we said, okay, let's focus on the chloride ingress models, chloride ingress models, yeah, ingress modeling, and then the analytical and the numerical models. Because analytical models we can only it's infinite space. Huh? Analytical models, they actually have an infinite space. They have no, you cannot use analytical models for a very thin concrete panel, which is submerged in the water and has a chloride load from two sides, because it will, finally, it will start to influence each other, the chloride profiles, right? They will overlap in the middle. So those things have to be taken into account. Finally, the benchmark, we selected those two benchmarks, the marine submerged and the road spray as the basic benchmark cases. So what is also important is what we did not consider. So we did not, first we wanted to start with service life and all those ideas, but we all skipped that. So we said, okay, we only focus on chloride ingress modeling and not on service life or cracks or corrosion or all that, those kinds of consequences almost of chloride ingress. That is what we did not consider in this study. Yeah, so what then finally, what is left? You can say, if you don't consider that. So what is left is then only a model with input and output. Yeah, and if you go from the input to the output, you can do a prediction, right? In this way, in this direction, you can do a prediction. And actually the other way around is what you need for your calibration. You need output data, you need experimental data to calibrate your model, and then you can do prediction, which is actually very important because this will increase the quality of your predictions, right? So the calibrations, you can see it more or less as this. I draw it in black, this model, because many models are black boxes. And if the model is a black box, it is even more important to understand the output and what input do you have, right? Normally we only look to the output, but the input is creating the output. So this is very important, and I will also explain that later when we see our results. The models actually to describe the chloride ingress are not so complicated, and the formulas, right? So the differential equation is this fixed second law, is this differential equation, second order, time and space dependent. And then we have this apparent diffusion coefficient, which is actually a constant, but we all agree that this is also a time dependent, that you can describe it as a time dependent function with this famous aging factor. Yeah, the advantage of this analytical of this differential equation is that you have a constant diffusion coefficient officially. Then you can have an analytical formula, which is very useful for practical purposes, and that's also what we use in this calibration set, in this benchmark set. We also have, there are many models there, they are very complicated. They solve this differential equation by numerical tools, numerical solution strategies. And then if you do that, you can also take some extra components into account. For instance, the binding or the convection. You can make it as complicated as you want. Binding is a thing that some models have indeed, but then you need a binding, binding function. How much chlorides are bounded and how much are free in the pore solution. Right, so this you can go more complicated. You can even more complicated. You can look to the individual ion species and use an Nernst-Planck equation. That's also one of the modelers have this approach, and that's also what was in. So it was a whole a good representative representative set of models was available in this technical committee. So the question is then, what are these? What is the performance? What is not what is a good model or what is a bad model, but what is finally, how do models respond to different situations? And that is actually what we try to answer this question, and which model responds best in marine submerged case, or which one do you need when you have a road spray case. Yes. Here you see an overview of the table that explains which models are used by the which different models are used. And then we have these analytical earth function models, and also then these numerical models. So which is numerical and which is analytical, you can see here, indicated by A or by N. N is a numerical model and A is an analytical model. And then if it's semi-infinite space, that is then analytical. Or when we have here both ingress from both sides, you can also do with a numerical model. A numerical model has more flexibility. Yeah, all the details on this are, of course, in this state-of-the-art report. Here, chapter 2. Chapter 2 is providing very. We discussed a lot actually on chapter 2 how to set up this, but finally we decided to first give an overview on different models which can be used for chloride ingress modeling. That is this, right? You see this, all kinds of earth functions, but also the numerical solutions, square root models. So from very simple to very complex, and also the physical models where the ion transport is explicitly mentioned. Also the interaction with the matrix, or the binding component, is also mentioned here, and also the saturated conditions. Boundary conditions, of course, very important, are also mentioned. And then finally, this chapter ends with a list of the models used in the benchmark. That is here, models used in the work of the RILEM TC 270 sim. So that are all these 14 models. They are described, the details are described, and also the typicalities, so what is very typical on this model is described, so that you really have a good idea when you look to the results later, that you know what kind of model is this, and what is special about this model. So then when we look to this marine submerged case, you can see that that we have the experimental results, the mixed design. So we provided to the modelers these curves as a percentage of the mass of concrete. So this is chloride, total chloride, measured data from this marine submerged benchmark case, but also as a percentage of the binder. And then for 0.6 years, 1 year, and 2 year, and then at bottom and the top. So we give this data to the modelers, to all these modelers active in the TC, and then we also provide a mixed design information, everything you need, temperature to do these calculations, right? To do these simulations. And then we ask them to calculate the 5, 20, and 100 years chloride ingress profiles. We did some circles. We need some iterations in the beginning to get this so far, but finally we asked this to the modelers. So then we can show you some results, what we got back. And that is, this is the 5-year result. And here you see that, so we gave them the data up to 2 years, no? And this is to 5 years. So there's already a 3-year prediction in the future, in time. And you see here the list with different models. I think this is really very great, yeah, that everybody participated in this benchmark. Really nice bandwidth, and I think this is very good result. Then after 20 years, you see the scatter is already a bit bigger, and in particular, the analysis of why this is bigger is in the report. And then after 100 years, you can imagine there is really a big unclarity about the scatter. Why are these results so? Because the differential equations are not so different. The differential equation is the differential equation, right? But how is it possible that the results are so different from each other? That is what we were asking ourselves, and then we had the idea to do a reverse analysis. So we took all the data we collected, and we did a reverse analysis to see what the input was. I told you before, the output, you can control the output by the input. So we did a reverse analysis, and from that reverse analysis, we got these results. And you see here the chloride surface concentration. I was really surprised by this, because I thought everybody, we gave them the measured result, the measured data from this Sweden test, experimental test data, and finally we got back this input data. So everybody has a different perception on how to calibrate these curves, right? And then finally ending up with these kind of chloride concentration, surface concentration values, ranging from 3% to 6%, almost 100% difference. And this also for the diffusion coefficient. We got the diffusion coefficient from 2e minus 13 to 1.6 e minus 12. So a whole big range covered by these models, which means that the input is here is very important for getting a very concentrated output of all the models. Yeah, that's what we learned from the marine submerged. Then we went further to the road spray. Yeah, so the road spray is the idea of this road spray benchmark case is that we would see whether it is possible to predict results, to predict the chloride ingress for a non-constant chloride load. So you have here the chloride load. The idea is that in the winter you have the de-icing salts, and then when the cars drive through the water, and then you have this splashing, and then you have only during certain traffic, right? Depending on the velocity of the cars, of the vehicles, depending on the salt, on the temperature, so a very many uncertainties. Where in this are actually in this calibration. So this is more a conceptual approach, because it's very difficult to predict in the future the chloride ingress, because you don't know the weather, right? So everything is weather dependent. We cannot predict the weather for 1 week, and also certainly not for 100 years. But we tried and see what were the results. So this is everything was very nicely provided by Jan Bishop. All the data you see here, the E3, E1, that are these different panels. The information for the different panels here: compressor strength, capillary porosity over 7, 28, 90, and 360 days. We also got from Jan the weather data, temperature and relative humidity, and then over 5-6 years, just to see a scatter, get an impression as a modeler for what is the weather in that particular area. Also here the monthly fluctuations of the precipitation, and you can see here that in the average fluctuations in precipitation is year. This is the year, right? The month of the year 12, and then here you see the millimeter on average precipitation, so that also these panels will be, of course, catch some rain, and the surface of the panel will be influenced by that. Finally, also the chloride. Yeah, the de-icing salt. Here's the NaCl. How many kilogram was sprayed on the road, and also here the total snowfall for these years to see, right? For modelers, this was the input what we gave to the modelers, and then finally they are asked to give a prediction for this situation. What we also give them is the next slide is the measured chloride input profiles for this. This is the height, right? 20 centimeters above the surface, and this is 1 meter. This result here, and this went up to 21.8 years. It started 1.6, 4.4, 16, 17, 18, and then 17.9, and then 20 21.8 years. So this is what we gave them, the data, and asked, of course, can you give us again a prediction? So first was we had a lot of discussions on this, how to interpret this, and also what to do, right? How to model this. This was the first modeling approach done by Lars Olaf Nilsson, and you see here he tried to do the first assessment. Actually, the results are very good, I think, because he tried to clarify which parameters are here important. And then in terms also of because you have the chloride load is only a few months, or maybe 1 or 2 months. Of course, with climate change, it will every time be shorter. And then during the year you have the rain, and it can happen that many chlorides which are in the pores at the surface will be washed out. That's what he also took into account. So, and he did a very nice analysis. More details are in the book on seeing what are, do you have to take that into account or not? All those details. We have here also from COE, they had a very nice prediction, and also tried to do the prediction for 100 years. Yeah, so from 1517 and also for 100 years prediction. Is that what's done? I think the results are very good. Here, the Klinkom model from Tang, Professor Tang, he also did a 100-year prediction, and you see also that at the surface this washout effect or carbonation, but also carbonation effect you have of course as well. But Lars also said this washout effect can also be relevant. What we have more is here from Serema. There was not a prediction to 100 years. They also only tried to simulate the current state, right, up to 21 years. I think the result is also very good. And we have here also from QF, he had a different approach. Results are also quite okay. And with the double multi-model, there were different other issues that play a role in this model. And here you see also for 100 years, but I think the results are also quite good. But you see also here the complexity of the whole modeling approach, what you need to how sensitive the parameters are, and how difficult it is to get a good simulation prediction. Yeah, finally, we had all this information, and we came up to conclusions. In the book, if you read it, you see there's some general conclusions, also some guidelines, some ideas for calibration, and outlook and recommendation. In general, it is actually what we did is when you look to the conclusions, it is that we have this marine submerged and road spray benchmark case is what we tested. We can calculate the analytical and numerical models, and we propose then the guidelines for calibration. But in general, you can say that the prediction accuracy of these models, they can only be improved when you improve the calibration. And actually, more specifically said, is that we need actually a calibration set, but with a procedure how to calibrate models. And if everybody uses the same calibration procedure, the input will be more controlled, will be more accurate, and then the output will also be better. I think the scatter in the output will also be better as well, at least for the marine submerged case. Yeah, that's what the final results were. You see, many meetings, many discussions, and I think the final result was very nice. I hope you will read the book, or at least see, download it and see what we did. And yeah, then the predictions will be more accurate in the future. Okay, thank you for listening. If you have questions, please feel free. Bye-bye.